Hey folks, how are you doing? Doing all right. Getting by. Yeah, it's hard to tell whether it's night or day sometimes, but good day. Yep. I'm trying to remember. Oh, all right. What element of that? Let's take a look. Graphs. That's not the one I want. Oh, you didn't have to make them look pretty, but thank you for that. Do appreciate that. Yeah, I mean it's hard to get like the lines, you know, nice looking and the fonts nice looking and stuff like that. I mean that's kind of above and beyond, but thank you. Yeah, and labeling them, of course, because yeah. Well, I it would be nice, but you know, I also am recognizing that it's challenging, particularly under these circumstances. But thank you. Good stuff. Um, cool. Um, I have, I will, I'm delaying a little bit posting solutions for those things. I'm waiting for someone with who's a little bit late with some of it. That's the main thing. Uh, cool. Well, let's see. I know at least one person couldn't make it. That would bring six. Then we're missing a couple more people. Up, oh, one more. Derek, and hopefully we'll get the last person after that. Good day, Derek. Just to go over things, right? Last week, final week left to go. So last little bit of reading with a warm up. I may have some other stuff that I'll ask you to skim. I won't be assigning additional warm ups beyond this one though. I realized I forgot to post the homework, so I will post that a little while later on. Um, and there'll be a quiz that has a lot of overlap with the last quiz that we did. Again, just kind of like, hey, let's pay attention to Maxwell's equations and a couple other relevant things, but that's about it. Um, I'm going to try to make it even simpler than the last one. Okay. So with that, actually, what we added into the mix last time, what's going on when you have waves inside of conductors, not perfect conductors, because you can't have any electric field in a perfect conductor, but in materials where there is some conduction, what we saw is that you get absorption. There's a spot. Yes. Okay. I will do that as well. Yep. Um, uh, yeah. And in order to accommodate that conductors, we had to add in complex uh, wave vectors into the mix and complex. Uh, yeah. So what we're going to do now, and we saw in the conductors that there was a phase shift between our electric and magnetic fields, and that we had, as they went along, the field attenuated, it dropped off exponentially. So now we're going to take a look at materials known as dispersive media. So that's material where the properties of the material are no longer just constants. They actually depend on frequency. And what we're going to see is we actually are going to end up having to use not just, not just the varying parameters. It's actually going to perforce required to include absorption. And so we're going to be using these complex functions the way we did previously. So let's get into it. And what we're going to do is we're going to talk about, well, what does it mean, right? If we've got different speeds for different frequencies, what are some of the consequences of that? And then we'll look at the mechanics of it at the microscopic level. And it's going to be kind of involved, but part of the point is to show you that some of the connections between, like, basically your Fun-2 oscillators and waves, right? Oscillations of a mass and a spring, very much connected to waves, which are connected to, in fact, electromagnetic waves, and the power of, like, this complex notation. So anyways, just to, whoops, wrong tool. Right, so far, right, what we've been doing is having our epsilon, our mu, our n constant. Right? And when we say constant, that's for every wavelength. Right? But usually that's not the case. Right? We start out simple, like we often do. So usually, right, it's epsilon as, I'm going to write frequency actually, right? And we can relate frequency and wavelength. Epsilon is a function of frequency, mu as a function of frequency, and so, right, and we know that we can relate those in turn to our index of refraction. So if those are functions of frequency, index of refraction is going to be a function of frequency, right? We're going to keep things simple, though, a little bit simple, though, right? And we're going to, again, a lot of the behavior is dominated by the permittivity, not the permeability, right? So basically the electrical behavior, right? And so we're going to say, hey, let's take our permeability, magnetic permeability, and make it, just look at cases where it's still pretty close to the permeability of free space, right? And so then what that means is what remains is our index of refraction. The mu part cancels out, and we're left with just square root of epsilon over epsilon naught, right? And that is our relative permittivity, our dielectric constant, right? So index of refraction, so long as there's no weird magnetic behavior, index of refraction is roughly equal to the square root of our dielectric constant, right? And so what that means now, though, right, is right, if we've got index of refraction that's a function of frequency, what we have is what's known as dispersion, right? A different index of refraction for different wavelengths. So it's slightly different speed for different wavelengths, different frequencies. So let's call this dispersion. Dispersive's the adjective. Can you think of a situation that you've seen before? I meant to pull up a picture of this in advance. A situation, an object, in optics, where dispersion is a key part of it. Yes, the pink, exactly. That's what I Googled prisms. Got some that were real prisms, some that were the Pink Floyd logo, right? So, right, you got white light coming in, and then it starts to, since the index of refraction is different for the different ones, right? It starts to separate out. So here, I don't want to spend too much time on this, but You get the idea. Woohoo. I'm having too much fun with this, though. That's an exaggeration right there, of course. But different index of refraction for the different wavelengths, different colors. So, all right, what does this actually mean for us? So we've been dealing most of the time with a sinusoidal wave, right? So, whoop. Has one frequency, right? But we can have other types of situations. We can have something. I'm drawing a wave, and I know you can't see it as I draw it. A wave that increases and then decreases in amplitude. So I can even draw like an envelope that maps out what's going on with the amp of the wave as we go along. Like that. Right? And so we call something like this a wave packet. So in order to make something like this, we have to combine many frequencies. Right? And we just said they're going to be traveling different speeds. So what's that going to do to our wave packet? So it can spread, it can shrink, it can even change its shape. Right. Those different frequency components traveling at different speeds. So we need a little bit more complete language to describe this. So here, let's talk about the speed at which one of those frequency components moves. And we've seen that we make it up, you know, are there multiple frequency components, even an infinite number of them, right? So our single frequency component, we call that the phase velocity. One way to think of it is, right, you have a well-defined phase in something like a sine wave right here, right? We know what the phase is. Here, though, right, it's actually a bunch of different waves combined, a bunch of different sinusoids combined, potentially with different phases. So you can't say, well, this is the phase of this thing right here. Well, and also you need to have like a well-defined, really clean function in order to have a phase of these oscillations right here. Right? And so this right here is what we've been using for our definition. Oops, I left out the over. Let's do this differently, right? I don't like that. Again, I just, nope, that doesn't work either. I got to actually use the right symbols. I got over K. Cool. Then the dimensions actually work, right? So this is right. We use this relationship already, right? And it didn't matter because we were mostly dealing with sinusoidal waves, so it was just that one for frequency. So that was fine to talk about the velocity because the phase velocity was the velocity of the whole wave because there was only one frequency there. But for a wave package, the envelope, that orange thing that shows overall, the wave packet envelope, right? We call that the group velocity. Well, hey, it's the whole group of them that get frequencies that get together to make that wave packet, right? And so we're going to give this a special letter. Sometimes you write VPH for phase velocity. and v sub g for group velocity. If there's no subscript, we'll do, then that will indicate our phase velocity. And when you've got a nice just linear relationship, right, we can see if there's just, if you've got the same v for every frequency, then you could actually say, well, okay, omega is equal to k times v up here, and then when you take the derivative, d omega to dk, you get v for your group velocity too. But we can also have different, but if we have a different v for different speeds, then you no longer can say d omega dk is just equal to v, because v will change with k, with our wavelength and with our frequency. Okay, so let me take a snapshot of this, and I'm going to show you a picture of this, no, not a picture, an animation that I made of this that helps us understand what these two different velocities are. Okay. I'm going to have to share a Mathematica screen, so that it'll lose this. That's why I make sure to save it first. Okay, so we got this right here. Let me stop sharing this and switch over to my Mathematica. Let's see. Oh, got too many applications open. Okay, I'm going to wait to see that it actually catches it. Okay, cool. All right, so what I've done is I've made cosines right here, and with different speeds, right? Because we could write this as kx, plus or minus vt. And so I've got a different speed for this second one right here, and then I'm adding them together. And what happens when we add two waves with different frequencies? You get beat notes. And so here, I'll do the simple animation first, right? And so we see, yeah, this doesn't actually, oh, that was in the middle. So you see the waves and you see the envelope of the beat and the waves themselves moving along. But I'm going to actually make it a little bit more complicated, where I can separately adjust the phase and group velocities down here, and it'll be a little bit easier to see what's going on. So this is I'm going to start this off right here, and all right, so if we look, we can see how the envelope, the group velocity moving along at this speed right here. Let's track one particular wave starting right here. I'm going to track this point right here, and notice that it's moving, but it's moving a little bit more slowly, definitely a lot more slowly, about several times slower than the overall envelope, right? So the oscillations, the fast oscillations of the waves within are moving more slowly, traveling more slowly than the overall envelope is moving. And I can reverse that if we wanted to, right? We can go, let's make this like this, bump up the group. Right, so now I've got the envelope. Well, that was moving more slowly before too. I'm sorry. I want to go my phase velocity so that, oh, I've got a weird relationship between them. That's what it is. I can even make it so that one of the velocities is backwards while the individual waves themselves are still moving forwards, right? The single frequency, the carrier frequency is moving forward, but the beat note, the envelopes are moving backwards. And so that would be, right, we can have all kinds of different relationships between them. All right, so getting a little bit more comfortable, right? The speed of the of how quickly those oscillations are moving along. That's our phase velocity of the main frequency in the wave. The group velocity, but you could also break it up into the velocity of each of the individual components, and they would have different phase velocities. The group velocity is the velocity of that overall envelope right there. Let's go back and actually talk about these things a little. We're not used to thinking about having two different speeds, but it turns out we can have a whole bunch more than that too. All right, so one of the things we can see, right, so describing these different aspects of our wave. We can even have some of them that are greater than the speed of light that we usually talk about, c. So long as they don't violate causality, speed of information transfer, which is often the same as energy transfer. And I'll give you an example. Like, how can we have something faster than the speed of light? Like we talked about some with electromagnetic waves, but I mean, here's a really simple example. Suppose we've got someone standing here at point A with a flashlight, right? That's shining a beam out like this, right? And here, this is, let's make this like 10 light years. Here's planet B, and here's planet C. Then they're one letter apart. And here's, again, that's also 10 light years, right? And so the person on planet A, though, takes their, so probably not a flashlight, probably like a laser, takes it and over the course of 1 second, changes the angle of the flashlight so that instead of pointing from B, it points to C, right? So what we could do is we could from planet B to planet C, these are different star systems, right? We see that spot move along, and it takes 1 second to go 1 light year, right? So the speed of that spot is like 10 to the 7th times greater than the speed of light, because it traveled a full light year in 1 second. Well, that's fine, but there's nothing that happened on planet that caused that right here. There's nothing that someone here on planet B could do to use that to send some signal over to here. Really what happened is person A did something quickly, and it took 10 years to get here, and 10 years plus a second to get over here, right? And that's, there's nothing, no information, nothing the person A did affected what happened at B or C, faster than the time it took light to travel from A to B or from A to C, right? So nothing that violates relativity, but we're still talking about aspects of this wave that are traveling much, much, much faster than the speed of light. So that's just kind of like an extreme example. So we okay with that? Little weird, but all right. So let's list some of the different. There's actually, yeah, a little weird. But you just, to say, hey, we're told that, C is the absolute speed limit for everything. No, it's the speed limit for any causal relationship, right? That's what it is. So there's actually a paper, I'll post it later, in the American Journal of Physics from, I don't know, like 30 years ago, something like that, that lists it out. I think they call it like the 7 speeds of light or something like that. So, right, we've just seen phase velocity. And so here we'll write this VPH phase is equal to omega over k, right? We saw that. There's the group velocity. The group is d omega dk. And we'll do some stuff where we have omega as a function of k coming up later on. It'll be a little bit easier to see what this is about. Here, there is the velocity of energy transport. Here, we'll call this V, how about sub E? And this is going to be given by the magnitude of our Poynting vector divided by our energy density. That's supposed to be U. There's the C that we've been seeing all along, our relativistic velocity constant. And that, like, you can get from special relativity, like you can write out an interval for your metric. Right, and so it's specifically the C that appears there, right? And that's where we're worried specifically about causality and stuff like that. There's one that we keep seeing in this class. Right? It just first it kind of popped out of nowhere when we were looking at electrostatics and magnetostatics, and then it appeared in the Maxwell impairs law. Is that a minus? Yeah, that's a minus sign. So it's minus c squared over d squared, dt. I mean, minus c squared times dt squared. And so that s squared right there is called the time space interval right there. Whoops, I don't know what I'm doing here. Right, we have this ratio of units velocity from Maxwell's equations, epsilon naught and u naught, right? And then we've got this C, we'll call it C from the ratio, was the one that kept appearing like that. There's our signal velocity. So that's the speed at which information travels. And that's going to be hard to define, right? We had a question about that. What is that? I mean, maybe, as a function of time, your signal, so here that's time, your signal is coming to you, 0, 0, 0, and then all of a sudden it's on, right? The group velocity is the envelope velocity, yeah. So if you have something where it's 0, 0, 0, and then instantaneously jumps up to 1, that could be a discrete bit of information. right? And so you can see quickly that edge propagates along, but in order to do that, right, in order to make that discrete edge, you need infinite bandwidth in um, your transceivers, in your material, in your transmission material. So in your transmitter, in your transmission material, and the other thing is, yeah, and infinite sensitivity. Bandwidth is like that. It is the so for just passive transmission, it will be the range over which you don't get any attenuation, right? Or some version, or over which their attenuation is above some, is less than some level, right? So you don't kill off your signal. So the signal can propagate freely. In an amplifier, it's the range over which you get a decent amount of amplification. And notice I'm saying decent, that's a little bit fuzzy, right? Oh, and so the other thing is you need to check that there isn't any, right? We saw before that a lot of times if you had like a kind of a smooth Gaussian, there was information in that tail and the leading edge. So you have to make sure that there isn't a tail with information coming in that way. The other thing is for something where it's more like a smoother turn on like that, then you could say, well, instead of it's only 0 or 1 and we can guarantee that, you can say, well, how about maybe when it reaches 1 over alpha of the max, and then that gets even more complicated. Things that really, so that has other problems. Right, so that one's a tricky one to work with, but that's going to be particularly important, like if you're really pushing what's going on in terms of causality. If you've got a little bit more of a smooth wave packet, instead of looking at, but the wave packet still is getting distorted, so you can't just say, oh, the whole wave packet is shifting over like we saw before. We can talk about, well, where is the center of the wave packet, even as it changes shape. And even as it changes shape, we can look at the centroid and see how quickly it's moving, things like that. Right? And then again, that's going to really depend on the details of the situation. And of course, we could talk about other things beyond that, but those are just some examples. Yep. But there will not be a quiz on that. And that's like this particular author was writing about it that way, and other folks wrote about it that way, but that's not necessarily something that's going to be universally understand. It might even be hyphenated, I'm not sure, or might all be one word. Yeah, so anyways, as we're talking about these wave packets though, right, the part of the idea I want to get across though, right, you don't have to remember all these things. It's just remember that there are lots of different aspects of the wave with lots of different velocities that we can use to describe those different aspects. So that's in part why we started out really simple with just single frequency monochromatic waves. There will not be a quiz on this. I just want you to get a flavor of that. Right. Cool. So what I'm going to do now, and this is sufficiently complicated that I'm not sure that I will be able to finish it today. But let's take a look at the microscopic level at the mechanisms behind this, and this can actually help us understand some of the behavior, though, some of the relationships between velocities, group velocities, phase velocities, and even with absorption, which seems like it's something completely different, but it actually turns out it has to be related. That's where we're going next. Lots of different velocities. So, yeah. That's our goal right there. Let's figure this out. So let's actually see like what's going on at the microscopic level. We looked before at individual dipoles when we started out talking about polarization and stuff like that. That's going to be what we're looking at right now. So yeah, we're going to have our wave coming in. Whoops, our wave coming in like this, right? And we look at the electric field, right? It is oscillating. In this case, pointing up and pointing down, right? And what's going to happen is it's going to hit an atom, right? So here's my atom right here, and the atom has a big, fat, essentially immobile nucleus and a little tiny electron that's negative, and it's bound. And so we're going to pretend it's bound like by a spring. We're going to model it with a spring. Yeah, right. So it's going to have the electric field is going to come in and exert a force on it, and it's going to cause a displacement. Exactly, right? So we're going to have a driving force from this electric field, right? F, we'll call it little driving, right? And that's just going to be equal to, well, the electric force is Q times E, right? And if this is a wave, it's just got some amplitude times cosine of omega t right there. Oh, and we don't have to worry about the kz minus omega t part because we're just looking at the electron. So we don't have to worry about the whole spatial extent of the wave. We're just looking at the field at the electron, right? The field at the atom. So that's going to be whatever that Q is for our charge. We'll just have E naught, and we only have to worry about the temporal oscillations. Okay. So that's our driving force. Let's take a look at so the driving force is coming from the electric field interacting with this. Whoops. And so let's take a look at the spring, what it does down here. Right. So it turns out the electron is moving around in a potential. Where does the cosine term come from? Cosine, right? This is a wave, so it's oscillatory. There could be a phase offset, right? And it's oscillating with some frequency omega. And I'm ignoring the phase offset. That's not going to be important because we're going to have this go through many cycles. Yeah, from the electromagnetic wave, right? So it is the electromagnetic field E right here is given by E naught cosine of omega t, like that. And we're doing this in one dimension, so this is going to be what I've drawn as vertically. Cool. No, thank you for asking. And in general, like if I'm doing this and it starts and it's not making sense, then yeah, let me know. So here, let's do the binding. This is again my potential energy, which when we write the whole function, we call that potential. Right? And here, this is going to be as a function of x, right, or displacement of the electron. Right? And so it's going to be some weird, I don't know what the function looks like, something, I don't know, kind of like that maybe, right? But it turns out that that is really pretty close to, let's see how well I can do this, particularly if we look at small displacements. That looks a lot like a parabola. right? And so here, we can write this out. Oh, and this minimum right there, right? That is the equilibrium point. So if we stay, so long as we stay near that equilibrium displacement, then we'll have our potential as a function of x. Oh, okay, well, this is a really ugly looking function. I don't know, it's just something I drew by hand, but it's to represent the complexity of what's going on. But we can do a Taylor expansion. Yeah, it's an energy well, exactly, right? So the electron stays bound to the nucleus, right? The electron naturally hangs out around here. So this equilibrium position is near the nucleus, right? And then it can kind of slosh back and forth, and an external field will exert a force which could push it, and as it oscillates, it'll slosh back and forth like this. And if you had a super strong field, it could even rip it all the way out, right? And you could ionize the atom. We're not going to do that. We're going to look at relatively small oscillations. And so for these relatively small oscillations, we can do a Taylor expansion. And so we are going to write this here. Let's define the equilibrium position to be 0. So it's going to be equal to x of 0 plus, right, a linear term, du dx evaluated at 0 plus a quadratic term, right, times the second derivative of u, right? This is a Taylor expansion, right? But that's evaluated at 0, and then there are more terms, right? So first thing is, right, all we care about. Yeah, exactly, right? So what we're going to talk about right now is only going to work if we've got a relatively weak electric field. And of course, things get more complicated, which can mean, more difficult to treat, but also potentially more interesting if we have some electric fields. And that's why, yeah, so for a lot of stuff that we do, like, having really intense light makes you have new types of behavior. But we're just going to start out to get start off with something more familiar. Hey, how does light behave in regular light behave in a material, regular wave in a material, right? But yeah, just be aware that of course we can always remove some of our simplifying assumptions and things get more and more complicated. So the first thing is this constant term, right? When we're talking about potential energy, right, we can add or subtract a constant and it doesn't change any behavior. Right, all we care about really are changes in potential energy. So what we're going to do is define u of 0 to be equal to 0. I have to deal with it. Next term. Well, it turns out that first derivative right there is 0 because we're at equilibrium, right? That's the definition of equilibrium, is that there are no forces, no net force, on it there. And the force is the spatial derivative. Force is the gradient of our potential. All right, and so that leaves us with this third term right here. And I'm going to continue this up here, right? So we're going to say that our potential energy as a function of the displacement, again, we're making it an approximation, but so long as we don't have really big displacements, so really big electric fields, it's a good approximation. Right? Oh, and this is evaluated though at that equilibrium, right? And so it turns out, right, this whole thing right here, right, we're taking the derivative of a function, but then we're plugging in a value. So that right there is just a constant, right? Because we're evaluating it at a certain point. What is the curvature of that curve? Right. So now let's go back and write our binding energy. right? We wrote our not our binding energy, our binding force. We're going to write an equation of motion, right? So we've got our potential. Let's write a force instead. So F binding, right? And that, like I said, the force is the negative gradient, and we're just in one dimension, so it's the negative spatial derivative of the potential, right? And so, all right, well, if we look at this down below, and if we look back down here, this first term we define to be equal to 0. Second term at equilibrium is 0, right? Or near equilibrium, very close to 0. So then we're left with this term right here, right? And when we take the derivative, the 2 cancels half, and so what we have overall is negative 2 tx squared evaluated at 0 times x. Right. I'll just make a note. Okay. And hey, we said that second derivative of u evaluated at equilibrium is just a constant. So let's give it a name like k. Not the wave number. What does this k stand for? What is the name of that k? No, not k again. Yeah. Vertical line in subscript 0 means evaluated at x equals 0. So we take the derivative of the function with respect to x, and we plug in x equals 0. Plug in 0 for x. So kind of like doing an integral, and you write the vertical line at the end of the. You do a definite integral, and you write the vertical line, but you have a top and a bottom number to do the. You do the upper bound, evaluated at the upper bound minus evaluated at the lower bound. Here we just have one point at which we're evaluating it. So what is this k here, though? Different k. If we've got something bound in a potential well like this, we're approximating as a harmonic. So this would be the same k right here over 2, so 1/2 k x squared. And here our binding energy F equals minus kx. What is the name of that k? What's the words that are its name? F equals minus kx. You saw that first semester. Energy equals 1/2 kx squared. Hooke, yeah, with an E, H-O-O-K-E. Hooke's law, right? That's our spring constant. Woohoo! Right, we're modeling. This is why we spend all that time on springs. I thought I would call it something else. I'm going to call it a spring constant, right? It is, and if we remember, oops, I'm going to do something else, not with that there. Just ignore that. We have another relationship. I'm kind of running out of room. Minus, this is an omega naught squared x squared. That's a squared. Right. And in particular, right, what I'm doing right there, right, this omega naught right there is our resonant frequency. Here, we'll do it like this. Omega naught equals the square root of k over m. That's our resonant frequency. So if you were to jostle the electron and just watch it slosh back and forth at its own natural frequency, that is that frequency. Okay. So we've got this driving force from the electric field pushing it back and forth. If you displace it, though, there's a restoring force, this binding force, that's a lot like a spring, right? So we're going to model it with a spring. The other thing, though, is there's also damping that's going on. Right? And so I can write a damping force. And it always points opposite the velocity, right? So the electron is moving in the positive x direction, the damping force points opposite that, right? It's negative e. What makes an oscillator harmonic? If the force as you move away from equilibrium is proportional, linearly proportional to the displacement. And then you'll get one single resonant frequency, whatever size displacement you have. If the force starts to vary from, vary from linearly dependent, linearly proportional, then you can have, depending on the size of your oscillations, you'll have different frequencies. And so that is non-harmonic. It's not all just the same frequency. Anharmonic, actually, is what we call it. So it turns out, right, because of the power of the Taylor expansion, right? Taylor expansion, any kind of equilibrium, right, where you go to any stable equilibrium, if you stay relatively close, will look pretty close to a parabola, will look pretty harmonic. But as you start to get farther away, you deviate from a perfect parabola. And so it's larger displacements, the anharmonicity becomes an issue. So this is really, really starting to look a lot like the beginning of Fun 2, right? Where you had the mass on the spring and you studied the harmonic oscillator, the damped harmonic oscillator, the driven damped harmonic oscillator, all that stuff, right? So we want to eventually write this out into one big differential equation. So we've been writing over here, right? This was just force as a function of time. Here, this is as a function of x. It would be nice if this were a function of x2 or x and t. Well, yeah, we can write v in terms of x and t. That's fine. We can write this. Right, and so here, let's give these couple things names right here. That's a gamma. That's our damping coefficient. Tells us how quickly does the energy get removed? How quickly do the oscillations die down on their own? So why is there damping in the first place? Well, it's because if we've got the electron oscillating, then it radiates electromagnetic waves. And electromagnetic waves carry energy. Radiates. Right? So if they're carrying energy away, whoops, then we can say that removes energy. And so what's got to happen, if energy is getting carried away, then the energy of these oscillations has to decrease as it gets carried away. Okay, so now we're ready to write out a differential equation, an equation of motion. And so what we're going to do here, let me just leave a little bit of space. We're going to write out MA, which is our net force, F net equals MA. And our net force is, well, we've written three forces down, right? There's the binding force. How do I determine that the electron is moving? Well, there's a force on it. It is moving relative to the nucleus. The nucleus is much, much more massive. So nucleus has the same net charge as the electron, right? Because we're dealing with net neutral atoms in general, or even if they weren't, right? It's about the same charge, right? So, but it is a couple thousand times, or multiple thousand times heavier. So it barely moves. The electron moves back and forth, right? But that's not even all that particularly important. We've got the relative motion is what's most important. But really, all we have to worry about is the electrons moving. Nucleus barely moves. In other situations, if we're dealing like with a plasma or something like that, then we might want to consider that. But yeah, that's it for here. Yeah, and so the x in our binding energy is the displacement of the electron with respect to the nucleus. So we have the binding force, the damping force, and the driving force from the electric field. Okay. So I don't want to try to cram this in right here. I'm going to continue restart this on the next page. But yeah, while we're doing this, just have an appreciation that we are drawing very heavily on the beginning of Fund 2. Then we'll take it beyond. Give me a second while I'm snipping. I can't see. Right, and this is just a toy model, right? This is capturing only part of what's going on, but it's capturing the most important part. Those negative signs in pretty early, pretty casually, so they worked out, didn't you? No, they were all with respect to the right stuff. Which negative sign before I go on? Being accused of being sneaky. Like, are we talking about that negative sign? Binding and damping. Well, no, because this is a restoring force, right? It's a restoring force, so it had to be negative, right? You go in a positive x direction, the force pushes you back in the negative x direction. You go in the negative direction, it pushes you back in the positive direction. And here, the negative sign, yeah, that's because it opposes your velocity. It's like trying to move through honey or something like that, move through water, right? It's opposing your motion. So that's why we have those there. There's a good physical reason. All right, so here, let's just quickly rewrite that equation of motion again. This is ma equals F net, F binding, and whoops, bing is the short form of binding. And ding is the short form of damping. And F net is short enough. Now, all right, so let's actually write these all out in terms, expand the expressions that we had, and actually even the A, right? We want everything in terms of x, our displacement, and t, our time. So this A, our acceleration, is just the second derivative of x. Oh. Wait a second. Okay. All right, so our binding, right, we'd written this as m omega resonant squared x squared, right? And then our damping is minus m gamma v, which is dx dt. And then our driving force was q times the amplitude times oscillations, right? The wave is oscillating back and forth like that. So it's a lot easier, right? What is this? This is a second order differential equation, right? Nice ordinary differential equation. Nice to have all the x terms on one side, the t terms on the other side, and then it gets into a form that's really, really common. particularly for harmonic oscillators. So I'm moving the damping force over to the left side, and that's why we changed its sign. And I'm going to group, kind of write the standard order, decreasing order of our derivatives, and then our function, and then here's in terms of the variables in which our function is written. Right. And so, yeah, this is a really, really standard, ordinary differential, second order ordinary differential equation. Who just said something? Did I miss the x squared in the binding term? Yeah, that's a squared. Thank you. Very good. Right. Turns out, right, we've got these oscillations. I wrote this in terms of a cosine. Like, it doesn't have to be a cosine right here. It could be, you could have some phase in there. So in order to keep track of that phase, and actually the phase of the oscillations over here, let's use complex notation, right? We're already, I'm not going to say pros, but we're already have seen it. We're kind of familiar with it, right? And that will allow us, instead of using cosines, right, let's use an exponential. Right, so if I do that now, oh, and the other thing is I'm also going to divide through by m, right, so that my leading term is just the second, whoops, it's just the derivative. What I'm doing. So first term is d squared, dt squared, but we're going to do this of our complex function x. See that? Loving it. And we divide through by m, so the m's canceled in this term, right? So this becomes gamma d dt of our complex function x. That's supposed to be able to, right? And then over here, we divide it through by m, so I have just an omega resonance squared complex x squared. This is equal to, all right, here there's no m to cancel out, so this becomes a q over m e naught, and by writing it, and we're doing this with an e to the minus I omega t, like that. And we'll take this phase to be 0, so x's phase will be defined with respect to it. Just make life a little bit simpler. All right, so again, still, even though we're dealing with complex numbers, still second order ordinary differential equation. All right, and so we're going to get, it turns out that these are well studied, right? And we're going to get two parts to the response to this, right? So you got the electron sitting here, send in the wave, starts driving it back and forth. We get two parts to it, to the response. So there's initially what happens, which we call a transient response, and that fades away, and then there's just kind of the long-term behavior that stays the same, right? It's oscillating, but it's a steady oscillating behavior. So we call this steady state response. So, the transient response typically lasts, a few oscillations. So that might be few. Yeah, t goes to infinity, but we're going to take the physics form of counting. It's 1, 2, some, a lot, infinity, right? And so we're dealing within the a lot, which is more than some, which some is more than 2. So a lot is a lot more than 2. So once you get out beyond, it depends how careful. So how much more? Well, it depends how careful you need to be. For most things, out beyond 10 or so oscillations is fine. But for other things, yeah, you might need to go beyond that, right? So we're dealing with things like optical oscillations, right? You're looking at light and it's oscillating 10 to the 15 times per second. So within a fairly small fraction of a second, you've already gone past the transient response and you're into the steady state. So we're just going to concentrate on steady state. Of course, there's times when you might be interested in this transient response, and that's something you can look into. It's just that's beyond the scope of this introduction right here. All right, and so that steady state response then is our displacement as a function of time all that survives is oscillating behavior. Oh, I forgot my prop. All right, we'll have to see if I can get this to work without. Right, and it's got some amplitude. So oscillations with an amplitude. That amplitude is a complex number, though, right? So it's got both a magnitude and a phase. So let's write that out. Where did this come from? This came from differential equations, people having figured this stuff out before, right? So the important part here is that this is complex. So these oscillations are not the same phase. As the driving field. And that is generally true for damped driven oscillators. We can write that phase difference, and I think that will be the point where we take a break for the day. So the phase difference turns out to be this right here. Okay, and so let's just quickly draw that out. What does that look like? So again, this is my phase. Here's 0. This is my driving frequency as compared to my resonant frequency. So that's frequency 0. And here, let's mark right here, pi. So what we get is something where this goes like this, and right around here, it's increasing, and then it saturates like this. And so this is something that you can try on your own. And, oh, here, wait. Let me just break this. It's an arctan. So it's not exactly I mean, we can call that a sigmoid, which is just generally a name for these kinds of things, but specifically it's the arctangent. Here, I have a Lego pendulum right here. See this? I'm going to stop sharing this. Let me actually snip, and then I will stop sharing. This is, the Lego stuff is, yeah. All right, here. Got this. So now we can stop sharing, and then I'll end. All right, so we got my Lego thing right here, and you see me swinging it. So I'm going to drive it by moving my hand left and right. And so long as the frequency of my driving is, oh, and here, let's see that is the resonant frequency, right? It swings, a couple times per second is the resonant frequency. So if I move more slowly than that, it stays exactly in phase with me, right? As my hand moves, it's moving with my hand. So driving frequency low, yeah, it's moving back and forth in phase with my hand. If I start to speed that up, there starts to be a bit of a phase difference between them. And watch what happens if I go way above that resonant frequency. So see the resonant frequency, if I go way above that, right? Notice which way up it's going. When I move my hand to the left, the thing stays behind at the right. When I move my hand to the right, the pendulum stays behind at the left. It's exactly a pi out of phase with me, except that when I took this apart, it came into two pieces. So here, let's go like that, right? Exactly out of phase with my hand as I go back and forth. So that is true in general for our driven oscillators. Well below the resonant frequency, it's the oscillator oscillates in phase with the driving force. For well above it, it's 180 degrees out of phase. And we have this mathematical expression for the crossover region in between, where you're comparable to the resonant frequency with your driving frequency. So this is all going to have to do with the electrons, though, as the wave oscillates them back and forth. Yes, right? If you're resonant, then all kinds of stuff's going on, right? So what happens if you drive a mechanical oscillator right at the resonant frequency? If there's not much damping, the oscillations start to get really giant, and yeah, woo, gosh, the whole thing came apart. Yeah, Tacoma's narrow bridge is even more than that. It's not just that it was at the resonant frequency, is that as it oscillated, it created even more drive, and so it was this self-reinforcing thing. Yeah, but yeah, big catastrophic stuff. Anyways, big stuff happens. So I'm already over time again. Let's stop here, and I will see you folks on Monday, where we will make sense of this and see what its implications are. And then their implications are actually really cool. We can really start to understand stuff. No, I guess not, because we're still talking about chapter 9. Well, I will post on Blackboard, but we can post it. Let's push it to Wednesday, to Friday. I didn't mention it but it is on the schedule. Yeah, let's push it to Friday. Is good. I will update all that. Cool. Yeah, we are not quite done with chapter 9. I will see you all later. All right, take care. Yeah, okay, Nick, I will take a look at that. Urgent or not urgent? Or just medium? Oh, I'll take a look.